Hi y'all, so this video I'm going to go over the answers to test 1, and I do want to say, what do I want to say? Oh, I was in a different environment in the recitation video, so I kind of would go off the page a lot, but I'm back at my regular desk. I had to be in a different room so I could hear the door, but I'm back at my regular desk, so I'm just going to go right through it. Okay. So in which structure below does the central atom have a +1 formal charge? So let's identify the central atom here and nitrogen in this one. So carbon has starts with 4 valence electrons, and this has 1, 2, 3, 4 bonds around it, so that's 0. Oxygen starts with 6 valence electrons, and that has 1, 2, 3 bonds around it. Minus 2 lone pairs is 1. So this is +1, so that's at least one option for us. But more than one of these choices is an answer, so we have to do all of them. NH3 looks like this, so nitrogen is 5, minus 3 minus 2 is 0, 3 bonds, 2 dots. So that's neutral, and then D is carbon. And again, carbon comes with 4 valence electrons, and there's 1, 2, 3, 4 bonds around it. Okay, there we go. Let me see if I can't fix this lighting a little bit. That might be a little bit better. Okay, which one of these is the weakest acid? Weakest acid in all these are the same functional group, so they're all COOH, which is carboxylic acid. And so then we're going to look for either a resonance or inductive effect to tell the difference between them. And the weakest acid will be the one that is least able to stabilize the lone pair that's left behind. And so that would be the one with the least inductive or resonance effect. And there's one that doesn't have any inductive effect, and it's A. And all of these have the same resonance effect. There's no additional resonance. Like if one of them was on here, that would maybe help. But in this case, A is the only one. Otherwise, this has inductive effect, this has inductive effect, this has inductive effect, and this has inductive effect. But this has 2 inductive effects, but A doesn't have any. Okay, what molecule would you expect to have the lowest boiling point? That's the least intermolecular forces. So that would be dispersion only. So that would be not polar. Okay, so not polar and, not polar, or I guess dispersion only would be the least. Looks like all of these have some level of polarity, so then not hydrogen bonding. So this has a hydrogen available for hydrogen bonding. So if you had this, hydrogen's partially positive, and it could bond to the to another nitrogen, and so on and so forth. And same thing with this, that would be partially positive because it's bonded to the nitrogen. So H bonded to a nitrogen is partially positive, so it basically engages in superdipole-dipole. This is again a hydrogen bonded to a nitrogen. This answer choice D doesn't have a hydrogen bonded to anything, so it would only be able to do dipole-dipole interactions or dispersion. So that's the least so far. And then this also has hydrogen bonding. So, and I'm going to draw this shape for you just so you can see why it's dipole-dipole. That's a carbon, carbon, carbon. So this nitrogen is more electronegative than these carbons. What? Yeah. So it's pulling slightly towards it. And then also there's this lone pair right there. So there's like a bigger density as well. Bigger electron density there. So I don't know why I circled E. So D is the right answer because it's the only one that doesn't have hydrogen bonding. And B is the right answer on that. Okay. Which functional groups are not present in the following molecules? Okay, secondary alcohol. Secondary alcohol is an alcohol where the attachment point is bonded to 2 carbons. So right here, I see an alcohol that has a carbon on either side. So secondary alcohol is present. Secondary carbon, that would be a carbon that's bonded to 2 other carbons. I see one of those here and here, so secondary carbon is present. Primary halide would be a halogen where the thing it's bonded to is only bonded to one carbon, and I actually don't see those. So that's probably a pretty good bet, but I'm going to keep going just in case. Because sometimes you can catch yourself missing something if you keep going. So let's see. D is a primary alcohol. A primary alcohol is an alcohol that the carbon it's bonded to is bonded to only one other thing. So that's what I see here. And then secondary halide. This is tertiary halide. So this is a secondary halide. So there we go. Another thing you could do is go through here and you could say, tertiary halide is present here. I wouldn't worry about doing all the carbons. Secondary halide is here. Secondary alcohol, primary alcohol, and if you wanted to, that could make it a little bit easier. You would still have to check for that secondary carbon, but you'd only have to be checking for one thing. And you could see your primary halide's not there, so that would be the answer. Which answer choice correctly lists the acids in decreasing order? So I'm going to just start with A, and I'm going to say what the pKa of all these are. 15.7, 25, 38, and 50. A baller, that's already in order. Then I'll, just to check myself, I usually, because, I miss things a lot, 25 and 15. So 25 is a bigger... So we're going from most acidic to least acidic. So we want smallest pKa to largest pKa. So this is a larger one before, so that's why B doesn't work. This is got 50 and then 25 and then 38, so that's definitely wrong. 50, 25, 15.7, 38, so that's wrong. And then 15, 38, 25, so that's wrong. So I'm confident in A. How many carbon-carbon bonds are formed from the overlap of sp2 and sp3 hybridized orbitals? So basically, we're looking for, we talked about orbitals and then how they have the hybrid orbitals are tetrahedral in shape, and two tetrahedral orbitals overlapping, that makes a sigma bond, right? So this would be a sigma bond that's formed from sp3, sp3. But if there was a double bond nearby, like if this carbon right here had trigonal planar situation, and then it had an extra pi bond, we'll just draw the extra pi bond like this. So this is only sp2 hybridized. All these would be sp2, sp2. And this bond right here is formed from the overlap of an sp2 from this carbon and an sp3 from this carbon. So we're looking for, I would start with looking for all the sp2 hybridized carbons because they're less common. So this is sp2 hybridized, this is sp2 hybridized, this is sp2 hybridized, that's sp2 hybridized. Okay, and then we're going to see how many bonds does the sp2 go with the sp3. So this is sp3, this is sp3, this is sp3, and this is sp3. So right here, I see a bond that's overlapping between an sp2 hybrid orbital and an sp3 hybrid orbital. So that's 1. I see the same thing over here, that's 2. Now this sp2 and this sp3, that's 3. This sp2 and this sp3, that's 4. This one and this one, that's 5. So I see a total of 5 sp2, sp3 bonds. All right. Which molecule would have the lowest boiling point? Lowest boiling point is least intermolecular forces. I'm actually going to switch to my other pen. Least intermolecular forces. This one's kind of dying. So not polar is the best. And then if if they're all slightly polar, then you would do dipole, not hydrogen. So now let's look and see. For cis-trans bonds, if the pull is in the opposite direction like this, it'll cancel each other out. So I'm looking for di-substituted trans bond here. And I see that with C, this one would be non-polar at all. Now D has 2 pulling away upwards and only 1 down, so the overall dipole moment of that one is up. This has 2 pulling up and none really pulling away down, so again, overall dipole moment on this one is up. and this has one moving away, so the overall dipole movement on that is up. So this is the only one that has two bonds pulling in the opposite direction, canceling each other out, meaning it's not polar, meaning it only has dipole-dipole, meaning it's easiest to overcome that intermolecular forces, so then that would have the lowest boiling point when you're trying to separate those molecules out and turn them into gas molecules. Which pair of molecules is capable of cis-trans isomerism? So cis-trans isomerism, we usually look for di-substituted or two of the same groups on the same side or the opposite side, and then this would be like CH3, CH3, or whatever. Now, if it's di-substituted on the same one, like this, that's not capable of cis-trans isomerism. So that's what we want to look out for. But here, we have two hydrogens in the same, two hydrogens on the opposite, so that's one answer, but just in case, I'm going to keep going. This one is all sp3 hybridized, so that's fine. And then it can't do cis-trans, because that's what I mean when I say it's fine, I guess. It can't do cis-trans because it can all rotate. And then we have this one. I'll draw the hydrogens in. Looks like we have two hydrogens on the same side and two hydrogens on opposite sides. So my answer choice is D, more than one of these. Okay, which of these is a primary amine? So amines are a little bit different, whereas with halogens, you're looking to see, like, this chlorine is attached to two carbons, so this is secondary. With amines, you're looking to see what's directly attached to it. So this would be tertiary. Sorry, this would be secondary. And this would be primary. So we're looking for two hydrogens and only one R group bonded to it. So I see two hydrogens and only one R group bonded to this nitrogen. I'm going to check all of them just in case, because there's some multiple. This has two carbons bonded to it, and this has only one carbon bonded to it. So 1 and 3. And I want to say on this kind, you may have thought this was pretty simple on this exam, but this comes back up on your final and stuff, and people will always get mixed up on their final if they haven't reviewed that. So just try to keep that one in mind. Rank from most willing to give up a proton to least willing to give up a proton. So this would be most acidic to least acidic. And another way to put that is smallest pKa to lowest pKa. Okay, so I'm going to go based on what I know from the pKa chart. Just the carboxylic acids are usually 4 to 5. Both of these are carboxylic acids, so I'm going to come back to them. This one is 16 to 18, this one's 25, and this one is 9 to 10 usually on the carboxylic acid scale, because even though it's an alcohol, it's stabilized by resonance, which makes it a lot more acidic. Like once it loses the proton, it has that lone pair left behind, and that can be spread all around, so there's not as much negative charge in one area, meaning it's more stable. So what I have so far is just C is more acidic than D. Oh, wait. E is more acidic than C, which is more acidic than D. So if you just know that and that these are more acidic, let's see what we can get rid of. So ECD is what we're looking for the last three. So that doesn't have ECD, so that's not good. This does have ECD. This doesn't have ECD. Neither does this. Neither does this. So I bet answer choice B is correct. Now, if you don't have that test-taking technique, or if you weren't sure about E, you could even just make sure that C and D, the two largest ones, were last. So CD, 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 CD. Nope, there's only one that has CD also as the last one. But let's compare these anyway. These are the same functional group. However, this has a significant amount of electronegativity. 3 fluorines pulling electron density away. So I'm going to say, instead of this being 4 to 5, I'm going to guess this is closer to like a pKa of 1. So I would put B and then A, because it has no inductive effect, and then ECD. So BAECD, and that is my right answer. Okay, this one everyone got right in one way or another. So the question is, which is the weakest conjugate base, which must mean it's the strongest acid. And I'm silly, and I thought about that, and then I circled this one like a crazy person on my on the answer key, but that one's actually wrong. This is right, because the strongest acid is the smallest number, is 0. So my weird brain strikes again, and I don't know why I picked 52, but Because of that, I saw actually everyone either answered A or E. So I think everyone made the same mistake I did, actually. So everyone got credit for that, whether they answered it right or wrong, because I made a mistake. And I don't think if I make a mistake, you all should be penalized. So you're welcome. And thanks for getting it right, even if you kind of got it wrong. Okay. Next question, what is the hybridization and shape of the carbon indicated with the arrow? So this is positively charged. So to check to see if there's any hidden or implied hydrogens, I'm going to say 4 is the number of valence electrons that carbon comes with, minus 1, 2, 3 bonds equals +1. So this is positive, so no. Only what's shown there is what we have. So if there's only 1, 2, 3 bonds, then we only need 3 bonding molecular orbitals. So that must mean we used 1 s and 2 p's to make sp2 3 times. So sp2, and the shape of sp2 is trigonal planar because they all get 120 degrees between them. So my answer choice would be D. What functional group is not present? Okay, well, before I look at my answers, I'm going to say this is a ketone. This is an alkene, although technically, is that a functional group? Sort of. It's like a gray area. This is a ketone. This almost got me. This looks like a carboxylic acid, but this is a primary alcohol. It's actually attached to this carbon here, and then this is a ketone. And this is a 1, 2, 3. That looks like a tertiary alcohol. So which functional group is not present? Well, a primary alcohol is present. A ketone is present multiple times. A tertiary alcohol is present. I don't see an ether. Ether is when you have an R group and then an oxygen and then another R group. I don't see that. And then an alkene. So I would say answer choice D is the right answer. Okay, which reaction shown below would favor the reactants? The left side of the reaction over the products, right side of the reaction. So the way I think about this is weaker acid is always favored, and that's the larger pKa is always favored. So to look to see which side is favored, I'm literally just going to compare pKa's. So the pKa, so I guess you have to identify the acid on each side. So I'll start with that. This is the acid. This loses it to become CH3, CH2O minus. This gains it, so this is the conjugate acid. pK of this is 16 to 18, and this one's 50. So this side is favored, so the right side of the reaction is favored. Boom. This one's 25. It loses it to become this, so that's the acid. OH minus gains it to become water. This one's 15.7. Nope. This side of the reaction is favored. You could stop there, but I always like to check myself because I make dumb mistakes a lot. So, this is 15.7, and this is 25. I guess dumb mistakes is a bad way to put it. I make little errors where I understand the concepts, but I get questions wrong a lot, so I always check all of them. Okay. So this one's right because 25 is on that side, so that's a larger pKa. This one's 16 to 18, and this one I think is, is it 30? Is it 30? Might be 35. I should have that memorized. That one's weird for me. It's somewhere around amines of like 38, but I don't remember. Maybe it's 35. Either way, it's larger, definitely, than the CH3OH. I guess I could check. I have a pKa table back here, don't I? You can also see how much faster this test goes if you already have your pKa's memorized. H2, it is 35. Nice. Okay, 35. So larger than 16 to 18. And then this is a carboxylic acid. So this tests your ability to recognize the shorthand of this functional group and use the pKa table 4 to 5. And this is 16 to 18. So answer choice B is correct. Which of these compounds would have the highest boiling point? So that's the highest intermolecular forces. So I'm looking for hydrogen bonds. If I don't see hydrogen bonds, it'll be dipole-dipole. And then dispersion, the most highest surface area would be what I'm looking for. But I see an oxygen bonded to a hydrogen right there. So I think that's a good bet. I see oxygen here, but they're not bonded to a hydrogen. So there doesn't seem to be a hydrogen available for intermolecular forces. I mean, it would be strong dipole for sure. And if you had this soluble in, I don't think we've talked about this very much. If you had this with like this, for example, this is here. If you had this in water, it could participate in hydrogen bonding with the water, but it can't participate in hydrogen bonding with itself. So, and then same problem with this one, and with this one, and with this one. No hydrogens bonded to oxygen. So there you go. All right, how many implied hydrogens are present at the central carbon atom? So this is those hidden implied hydrogens again. So carbon comes with 4 valence electrons, and we have a negative charge, so it has to be minus something to equal -1. So 5 total. We have 3 bonds, so carbon minus 3 bonds minus 2 would equal -1. Because we can see the 3 bonds, so 4 minus 3 is 1, so you still have to take away 2 more to get to -1. I don't see, the only way we could have 2 more bonds is if there was 2 implied hydrogens. And tell me why that's not right. I'm going to assume you all said 5 bonds to carbon, either out loud or in your head, so the only other way we could do it would be 2 lone pairs. So 1 lone pair, 2 electrons, 4 valence electrons, minus 3 bonds minus 2 equals -1, so I'd say 0 implied hydrogens. Okay, which of the following species contributes more to the overall hybrid for the species in the box? So in this case, one thing I like to do first is get rid of anything that's not a proper resonance structure. And this bad boy has a hydrogen bond, or has a hydrogen atom moved right there. So we know that is not a proper resonance structure, because there wasn't a hydrogen and now there is. So that's just a different molecule. So no. Now we've minimized it down to just these 3. The other thing we know is whether or not this is a valid resonance structure, less charges are better. This has 2 negatives and 1 positive, so this is going to contribute less. So I've narrowed it down to where we don't have D and we don't have I. So it's either, why did I say I? 1. So it's either 2, 3, or the one in the box. So before I decide which one contributes the most, I'm actually going to decide which one is, which one of these are valid resonance structures. So to get from here to here, I'm going to say this lone pair had to move here because a new bond was formed, and this came here. And so that looks like a valid resonance structure. Nothing else changed. There's not too many bonds to carbon anywhere, so that's valid. Now I'm going to use a different color to get to here. I think similarly it would have come here, and then this would have gone there to make that lone pair there. It doesn't look like there's too many bonds to hydrogen. It didn't, for example, move up here, so that one looks valid to me as well. So all 3 of these are valid. So the next question is, which one's the best? Well, in general, the rule is the negative charge wants to be on the most electronegative atom. So I'm going to actually choose B as the right answer, because that has the negative charge on sulfur, and sulfur should be more electronegative than carbon. Okay. Compare the 2 molecules below. Which one is more acidic? Okay, so this one, I talked about this briefly in class today, but the big thing that I wanted you really to do was thoroughly explain why. So you could look at the pKa table actually, and you would see phenol. The shorthand of phenol is C6H5OH, and that's like in the 9 to 10 range. I guess we can look and see what it actually is. We don't have to say what range it's in. C6H5, C6H5, C6H5OH, it's 9.9. And then alcohols in general are, let's see, here's an alcohol 16, here's another alcohol 18. Yeah. Okay. So alcohols are usually 16 to 18, but phenol specifically is higher, like 9 to 10. And I asked you to explain why. And the way I would explain this is phenol is more willing, this would be like an ideal answer, to give up a proton than cyclohexanol, because when the proton leaves or proton is taken, a lone pair is left behind, not G, which can be more stabilized, I'm running out of room, by phenol, then I'm just going to abbreviate cyclohexanol. Well, no, I can write it out. Cyclohexanol. And then I'm running out of room, so I'll just say, so then the next sentence I'd say phenol is more, overall this says phenol is more willing to give up a proton than cyclohexanol because when the proton is taken, a lone pair is left behind, which can be more stabilized by phenol than cyclohexanol. And then I would keep writing and say, it can be more stabilized due to resonance delocalization, which means that the negative charge isn't concentrated in one area, it's all throughout, making an overall more stable molecule. Therefore, losing the hydrogen has less impact on the stability of the molecule. Something like that. That's what I would be looking for. If you just said resonance stabilization or it has more resonance structures, that doesn't really fully answer the question. It's not a thorough explanation, but I think I gave like 3 points for that. 1 for choosing the right thing, and then 2 points for that explanation. But 2 more points would have been given if you'd taken it just a little bit further. And for people who got to varying degrees of that, I gave them a little bit more points. Okay, next one. Draw the resonance structures of the following molecules. So I always start, one, I'm going to go ahead and draw in the lone pair here. And then I'm going to draw the hydrogens here. Hydrogen, hydrogen. Because a lot of times this helps people not to lose their hydrogens. Okay. 1, 2, and here, and then 2 hydrogens here. Okay, so I think this helps. So I'm going to draw the curved arrows. I'm going to start at the highest area of electron density. I'm also not going to look at anything that already has an sp3 hybridized carbon. So all of these already have 4 bonds to carbon that are sigma bonds, and since you can't break sigma bonds, that part of the ring is not going to participate in resonance. So if you drew any bonds down to here, that wouldn't work, because if there was an extra bond here, imagine if I'd drawn a bond right here, even if I broke this one, there's already 1, 2, 3, 4 bonds with that implied hydrogen. So if you made that mistake, I would practice having your implied hydrogens drawn in. So the first thing I think is I'm going to move this here, but if I do move this here, there's 1, 2, 3, 4 bonds to hydrogen, or to carbon. So I'm going to break that and put it on here as a lone pair, and I just go one step at a time. So if you can get to a stopping point, like here, we got to a stopping point. We stopped right here, and we're not violating any rules. There's not too many bonds to carbon. We can just stop right there. Then I'm just going to stop right there, and I'll draw the next structure. Because otherwise, if you don't go one step at a time, and if you keep going all the way around the ring, a lot of times what I see happen is people will accidentally miss middle structures or get themselves confused. So I'm going to draw everything in just to make sure. My implied hydrogen. So this has 4 bonds to this carbon, 4 bonds to this carbon, only 3 bonds to this carbon, but with the lone pair, it's a full octet. 4 bonds here, and then again, this part of the structure is not playing ball. It's not a part of the situation. Okay, so now I'm going to use a purple arrow to show that this comes here and this bond breaks and goes there. And we're going to stop there one step at a time, right? So we got our lone pair to go here because you can't have too many bonds to this carbon right there. And if that makes a double bond, then something has to break. So this double bond breaks. Can't be a sigma bond that breaks. And then we stop there. So I'm going to draw everything in just so you can see. This has enough bonds there. This has enough bonds there. This has enough bonds there. This still has a hydrogen, but there it's neutral. Okay. And then you want to ask yourself, is there anywhere else I can go? And I saw a lot of people try to bring this lone pair here, and that doesn't work because if you did that, you would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Overly full octet. So that doesn't work. So if you got these structures right and then you kept going, I subtracted minus 0.5 because you didn't see the overly full octet. So this is not a viable arrow. That doesn't work because this oxygen would then have too much. If it was sulfur, you could probably do that, but this is oxygen. And you can't break one of these bonds to go here to make it a less full octet because one, the lone pair would still be here. So then you just have 4 bonds in a lone pair, but also this already has 2 hydrogens. So you just kind of be making it worse and worse. So you actually stop right here. So to get full credit, you had to draw, I gave a point for each arrow, and then half a point for the right structure, and then a point for each of these arrows, and half a point for the structure. So if you got all this, you got 5, but if you kept going, you got minus 5. 0.5, not minus, totally 5. Okay, what is the hybridization of each carbon atom? So for this, we look at the sigma bonds. There's 3 sigma bonds. So S orbital, P orbital, P orbital must have combined to make 3 sp2 orbitals to get those 3 sigma bonds. And then your third P orbital, this is part of your double bond or your pi bond here. This is your pi bond. Okay, so, and both of them have that same situation. So they're both sp2. And this shape is trigonal planar, so it's just flat. For each bond, represent the dipole moment. So this is the biggest dipole moment, is this chlorine is pulling atoms towards itself. There is a slight dipole moment on each of these. It's much smaller. I didn't count off if you did or didn't put those because I mostly cared about this. And then the, so I did that. And then the overall molecule is polar because everything is pointing towards this chlorine. If there was a chlorine on this side, it would cancel out, but there's not. So what intermolecular forces would be present? Dispersion is always present, but if you didn't write that, I didn't count off because the thing I was really looking for was dipole-dipole. And I saw all kinds of cool stuff here on this, so I really appreciated it. So thanks for your answers. And if you didn't get points on that, please at least try to come up with something so I can give partial credit because I want my students to do well. I really, really do. Okay, well, I hope that was helpful. And if you have any more questions for me, please reach out and I'll try to make a video before your exam.